on TP 22 on the radiation properties of surfaces. So, TP 22 this is your third class on the radiation heat transfer. Radiation properties of surfaces. Let us assume this is the surface on which there is an incident radiation. This is your incident radiation. This is your reflected radiation. And this is your transmitted radiation. Let us suppose this is a surface on which the heat energy is striking, radiation heat energy is striking. That means, if a certain amount of radiation energy which strikes over a surface, then it is quite inevitable that some part of energy will get reflected, some part will get absorbed by this material of the surface, and some part of energy will get transmitted. So, accordingly, the IR, RR and TR stand for the incident radiation, the reflected radiation and the transmitted radiation. In this, there is some absorbed radiation also, absorbed radiation. So, this is a diagram which depicts or which throws an idea about the different radiation components. Different radiation components. So, if radiation energy incident over a surface from source, it means a part of this incident radiation energy will get reflected. This is the part, this is denoted by the Greek letter rho. A part will get absorbed, and this is denoted by letter alpha, which is called the absorptivity, and a part will get transmitted. A part will get transmitted. This is denoted by the letter Greek letter tau. So, the definition of rho that is called the reflectivity, that is defined as reflected radiation energy radiation energy divided by incident radiation energy. Let it be question number 1. Another quantity, that is absorptivity, it is defined as absorbed radiation energy divided by incident radiation energy, incident radiation energy. Let it be represented as equation number 2, and the transmittivity, that is the called tau, it is defined as transmitted radiation energy divided by incident radiation energy. So, if I add this reflected radiation energy plus absorbed radiation energy plus transmitted radiation energy, that should be equal in magnitude to the incident radiation energy. Definitely that should be there. So, this quantity rho, that is a quantity which is lying between 0 and 1, because the total reflectance, means if the nature of the surface is such that whatsoever the amount of energy which gets incident over the surface, if 100% of this energy will get reflected, that means the rho value is 1. However, the practical chances of obtaining all the energy as a reflected energy as equal to the incident energy cannot be made possible. So, this quantity is never equal to 1, that has been shown here, that is the 0 less than rho less than 1. Similarly, 0 should be less than alpha, that should be less than 1, and on the same guideline 0 less than tau less than 1. And also the third thing which can be derived from here, that is the value of rho plus alpha plus t is always equal to 1, that is always equal to 1, because that constitutes the whole part of the incident energy which got reflected over the particular surface. Hello, class 7. So, this is the, but the fraction of all these three things, that is the fraction which is reflected, the fraction which gets absorbed, and fraction which gets transmitted, that should be equal to 1. This reflection may be of two nature, as specular and diffuse. Either the specular reflection will be there, or the diffuse reflection will be there. The question arises, how these two types of reflection can be characterized. Let us suppose I am able to produce a surface where a certain amount of heat energy or radiant energy is being radiated from here, impinges on the surface and get reflected back fully. This is the perpendicular drawn at the point of incidence. So, let it, this angle is phi 1, this angle is phi 2. For the reflection, this phi 1 is equal to phi 2. So, this is the incident radiation, this is the reflected radiation. When such, this is possible only in the case if the surface has been polished to such an extent that there is no protuberances is there, no undulations are there, no defects are there. Under those circumstances, the law of reflection will be completely obeyed by this radiation with phi 1 equal to phi 2, and such type of radiation is what is known as specular radiation, specular reflection, and this is possible in the case of perfectly polished surface. In the case of the preparation of metallurgical samples to be studied in the compound microscope in the metallurgy lab, it is often customary to have an almost 100% specular type of radiation, specular type of reflection, so that the image or the phases which are there in the microstructure may be completely get revealed by the observer in the eyepiece. Another type of radiation is called diffuse radiation, an imperfectly polished surface. When a radiation from a source get impinged over here, so this incident radiation, definitely this will follow the law of reflection and some part will get in the phi 1 equal to phi 2 direction, but many components will get reflected in a haphazard way, and in a random fashion this radiant energy will get reflected. Such type of reflection of radiation energy is what is called as diffuse reflection. This is called diffuse reflection. This is in the case, this is possible in the case of rough surfaces. In the case of the study of the metallurgical sample under the compound microscope, if you will have this diffuse radiation, then the correct feature, the correct characteristic of any of the phase present in that particular material cannot be revealed precisely. Now, referring to the equation number 4. Now, referring to the equation number 4, referring to the equation number 4, if alpha equal to 1, that is the complete absorbance, alpha equal to 1. For this condition to happen, that is alpha equal to 1, it means the value of rho is equal to 0 and tau is equal to 0. This is the condition. A black body. This is the condition for a black body. However, no real surface has the property of a black body. So So, the question arises, how black body is approximated. This is our next thing, that no real surface has a property of black body. That means, in none of the black body case the alpha is equal to 1. It means must be some way, there must be some model by using of by the use of which an approximate black body can be considered. So, in order to visualize a black body on an approximate scale, what is done? In order to have an approximate visualization of a black body, a cavity is assumed in which there is a very small opening is there. This is a very small opening which is there in this case. So, what will happen in this case? Any heat energy which is entering this container, some part will get reflected, some part will get absorbed, some part will get transmitted in this manner. And some will leave the aperture. So, some will leave the container through that small aperture. So, by taking a cavity, with an infinitesimally small aperture, and assuming that the internal surface of cavity at a uniform temperature. So, a container is there with a very infinitesimally small aperture is there, and the inside surface of the container is at uniform temperature. By assuming or by hypotheticating such type of cavity, an approximate black body can be assumed. Any radiation enters the cavity through the small aperture, implies that incident rays get reflected back and forth by the internal surface. So, it implies that it can be assumed that all the radiation may be assumed to get absorbed by the cavity. By doing so, black body approximation can be modeled. This is the basic philosophy behind the assumption of a black body. Another important thing regarding the black body is the Kirchhoff's identity. This is the final task of the present class, that is the Kirchhoff's identity. So, next thing is the Kirchhoff's identity. So, as you know, the energy emitted by the body per unit area per unit time is called the emissive power. Is called emissive power, and this is denoted by the letter E, and E is a function of temperature of the body and the wavelength of radiation. Thus, it can be said, it implies that emissive power is specified for a given wavelength and temperature of the body It is denoted by EBT. Sorry, it is not by E lambda t. Sorry, it is denoted by the symbol E lambda t. This E lambda t is also termed as termed as spectral hemispherical emissive power. Radiation in all the directions, are taken care of by integrating the radiation with respect to directions over a hypothetical hemisphere over the surface. Because radiation will going on along all the directions, so this spectral hemispherical radiation radiative emissive power can be assumed to as the integral of all those radiations along all those directions which are available over a hemisphere put up over that particular surface. Another quantity epsilon called spectral emissivity is defined as epsilon lambda t, that is equal to E lambda t divided by E b lambda t, that is for the arbitrary surface divided by the same quantity for a black body. So let it be question number 5. And this equation number 5 E lambda t, that is in the numerator, this is called your emissive power of a body, and this quantity E b lambda t, that the emissive power of a black body. And also this quantity, that is the epsilon t, that is called the total emissivity, that is defined as E t divided by E b t. So further it can be written as E t, that is equal to integration 0 to infinity E lambda t dt divided by integration 0 to infinity E b lambda t dt. Let it be question number 6. emissive power of a black body is always more than any body and hence emissivity of any body other than black body, emissivity of any body other than black body is less than 1 always. This identity is called your Kirchhoff's identity. It is called Kirchhoff's identity. Now we are coming to the proof of this Kirchhoff identity. Let us come to the proof of this Kirchhoff identity. Proof of Kirchhoff's identity. Visualize the following physical model. The physical model is, this is your enclosure in which there is a sample body. This is your sample body. These are the entering heat flux. It is denoted by letter Q suffix I comma T. And these are the emissions. So this is called your ET. This is your enclosure. The formulation of the problem is placed in an enclosure at a given position and it has been allowed to attain a thermal equilibrium with the enclosure. Now at equilibrium, no heat energy exchange will be there. It means temperature of body that will have a constant value, constant and equal to the temperature of the enclosure and equal to the temperature of the enclosure. So we can write Et into A, that can be written as QIT into A into alpha. Let it be question number 7. Here QIT is the flux of incident radiation, A is the surface area of the body, and alpha is its absorptivity. Now the sample body is altered by a black body of surface area A and at same temperature. Then for thermal equilibrium to happen, this EBT is equal to A into A, that should be equal to QIT into A. Let it be question number 8. Since alpha is equal to 1 for a black body, so by dividing 7 by 8, so by dividing equation 7 by equation 8, you can write ET into A divided by EBT into A, that should be equal to 1, and that should be equal to alpha, or and since this ET by EBT, what is that called? This quantity ET divided by EBT, what is this quantity called? That is called the emissivity, epsilon. So ET divided by EBT, that is equal to epsilon, that is equal to alpha. That means it gives rise to the conclusion that at thermal equilibrium, emissivity of a body and its absorptivity are equal. That means, when thermal equilibrium is executed, the emissivity of a body as well as its absorptivity is equal. This is what is called the Kirchhoff identity. So, in the present class, we have gone through the radiation property of surface, we have an understanding of the emissive power, we have an understanding of the monochromatic emissive power, and also we have gone through the derivation of the Stefan-Boltzmann law to establish a relationship between the absolute temperature and the quantity of heat energy which gets radiated from a surface. So, in the next class what we are going to learn, that depending upon the orientation of the two spatial surface objects, depending upon the relative orientation, the quantity of the heat energy or quantity of the radiation energy which we are receiving, that is going to change. This is determined by a factor which is called the shape factor, and this is the reason that why in the cold season even the heat energy is being dissipated at the same rate from the sun, but due to the altered orientation between the sun and the earth, the quantity of the energy received by us on the earth's surface will get deferred, and we are feeling cold weather. Similarly, the same case happens in the case of the summer season also. So, the amount of radiation which is being received by you, the amount of radiation which is being receded from the source, that is related by a quantity that is called the shape factor. In the coming class, we will go through the concept of shape factor and how this concept can be utilized in order to evaluate the shape factor of regular geometries as well as regular geometry. In the next class, we will see. Thank you.